Welcome again. So you're supposed to have done a structural diagram of the area and looked at the different rocks and different formation exposed. So let's start with the topography. Let's talk about the topography. We have here a sort of, it's not a low relief, like we've got hills, we've got valleys. Typically the summits are around 4,000 feet in elevation. Valleys are at an elevation of 2,000 feet. So around 2,000 feet of relief, we're talking about 600 meters. So, you know, it's not big mountains, but there are definitely steep slopes around. The valleys tend to be broad, wide open. You have some gorges in a few places. So we've got hills, we've got valleys, we've got some relief. But it's not the Himalayas, but it's not the Bristol area neither. There is definitely some relief here. In terms of the rock types present here, there's not that many obvious unconformities. It's a sedimentary succession from the Paleozoic, starting in the Ordovician, going to the Devonian, and we have dolomite, limestone, sandstone, shale, so a sort of sedimentary succession here in this landscape. We don't have many evidence for faulting. There is a major fault here, and you're going to have to figure out its orientation and its flow because it's on the line of section. But what is the most obvious on this map is really the folding. The folding is very spectacular. You can see folding on a range of scale. You can see that through the symmetrical repetition of the beds, like around the axis. And you've got a range of scale. As I said, you've got here a very broad syncline, for example. Be careful, this color is not the same than this color. This is DM, this is DCH. So this is more recent than this one. So we've got here a very broad syncline, but we've got also very narrow folds like here, here. So we've got folding on a range of scales. We've got the repetition of the beds. We've got beds dipping towards the southeast. We've got beds dipping towards the northeast. And we can see that everything is aligned in that sort of north-northeast or southwest direction, suggesting a direction of compression like that. This structure seems to really affect the morphology of the landscape. So we've got rivers flowing typically parallel to the structures. We've got mountains made of anticlines, like Tower Hill Mountains. If you look at the deep direction, you will see this is an anticline. We've got mountains made of syncline in the syncline as well here, Warm Spring Mountain here. And we've got a very spectacular example of relief inversion here, whereby the anticline, which is an incline, is structurally high, represents a valley. So we've got the anticline has been completely excavated here, and the valley is flowing at the top of the anticline. Right, so that's my structural diagram. So I've tried to represent, again, put an approximate scale, orientation, say where you are. I've put Williamsville as an example, as a location, put the name of a few mountains, put the main rivers, and put the main anticline and syncline axis to illustrate that structuring. I think the way I've drawn them, they should be a bit more in that direction. But again, this is just to give you an idea of when you do your line of section, you're going to meet essentially a succession of anticline, syncline, faults, anticline, synclines, and so on. So what I'd like you to do now is do your cross section, remembering you will see that the main difficulty of this cross-section is not going to be the structural difficulty. It's going to be more trying to keep the thickness of the bed constant and the geology consistent. What I'd like to highlight also is that you can use dip and dip direction to calculate the thickness of the beds if you really want to, but in most places you won't have to, because the beds are quite steep. So if you imagine that you've got your topography like that, and you've got beds that are quite thin and steep. If the beds are dipping 50 degrees and you've got a contact here and let's say 50 degrees and a contact here, you will end up with, you will see that the thickness of your bed is going to emerge. You're not going to have much leeway. You're not going to be able to make your bed much thicker or much thinner. So a lot of the constraints on the thickness of the bed will come from the building of the cross-section in this area in particular. what I'd like to highlight for this section, so you have a lot of deep and deep direction symbols near the line of section or further away, so feel free to use these symbols to constrain your structure and constrain your thickness. Start from the youngest to the oldest, so you're going to start by putting that fault, so try to think about its orientation and dip. And what I'm going to ask you to do is, if you want to complete the succession down, some of the beds here are too thin to be represented to be represented on their own, because this is 162,500, so 1 millimeter on your line of section is 62 meters. So if you've got a bed that is 30 meters thick, it's going to be half a millimeter. So basically OM and OMC, you can put together OM and OMC here, these two, and you can put together OL and OLU, these two formations that are very thin. So like that, it's going to make the building much easier. So off you go. And what I'm going to do for in the next video is, well, let's start talking about the fault, and then I will let you build your section, and then we will go through the difficulties starting in that area and going all the way to the end of the section. Okay, off you go.